Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions, to promote the use of the best available methods, and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by clicking on the chat icon located in the lower right-hand corner of your WebEx window. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Dr. Moyer. Today's speaker is Dr. Richard Hooper. Dr. Hooper is Professor of Medical Statistics at Queen Mary University of London. He has a 30-year career in health services research as a medical statistician. His current research program aims at driving innovation in the design of randomized evaluations of health interventions and quality improvement programs, including step-wedge trials and other novel approaches to clustered trials, an area in which he has already established an international reputation. In 2019, he was awarded a senior fellowship by the Healthcare Improvement Studies Institute in the United Kingdom to develop and promote innovation in trial design as a key aspect of health improvement science. He's the co-director of the Pragmatic Clinical Trials Unit at Queen Mary University of London, a United Kingdom registered clinical trials unit that specializes in evaluating interventions as they would be delivered by health services. It's my very great pleasure to welcome Dr. Hooper.
Thank you very much, Dr. Murray. It's my pleasure to be here. Just to tell you how this talk is going to go, I'll start with an introduction to what I mean by stepped wedge trials with continuous recruitment. I'll talk a bit about why we might need new ways of thinking about these trials. I'll talk briefly about some methods that we can use for studying optimal designs, and then I'll look at some particular design problems and their solutions, and finally make some concluding remarks, if not some actual conclusions. So stepped wedge trials are everywhere at the moment, it seems, and increasingly proposed for almost everything, which has become something almost of an in-joke in some parts of Twitter. On the left here is a fairly reasonable suggestion that we could use a stepped wedge design to evaluate vaccination programs for COVID. On the right is a proposal to use a stepped wedge design for evaluating dresses with pockets. And before stepped wedge trials become a parody of themselves, it's worth taking a step back, thinking about what stepped wedge trials are, how they work, and where they can be useful. Stepped wedge trials are usually trials that are randomized in clusters or group randomized trials. And the clusters are randomized not to one treatment condition or another, but to a sequence of treatment conditions over an extended interval of time. And in particular, in a stepped wedge trial, those sequences are in some sense unidirectional. So you might be able to cross from the control condition to the active intervention condition, but you can't cross back from the active intervention condition to the control condition. And the reputed advantage of stepped wedge trial designs that I often see trotted out is this, that everybody gets the intervention. Now, I personally dispute this logic, but I'm fighting a battle of one person at the moment on that. Unless you're following a cohort of individuals, then it's not true that every individual participant in a stepped wedge trial gets the intervention. And in any case, it's fairly easy to do a trial where every cluster gets the intervention. You just have to use some kind of waiting list control design or offer the intervention to every cluster at the end of the trial. So for me, this is not the reason that we do stepped wedge trials. But there are two very good reasons that we might do stepped wedge trials. The first is that in some instances, they're more statistically efficient than a parallel groups cluster randomized design over the same time interval. And the other reason is there may be some practical advantages to staggering the introduction of the intervention. For example, there may not be enough of the intervention to deliver to half of the clusters simultaneously. The first ever stepped wedge trial was the Gambia hepatitis intervention study, which was described in 1987. And in the GHIS, 17 regional vaccination teams in the Gambia in Africa were randomized to different schedules for rolling out a hepatitis vaccine for newborn infants. And this schematic is adapted from the protocol paper. And you can see in the schematic that the timetable for implementing the hepatitis B vaccination program produces this visual impression of a stepped wedge, which is where the trial design gets its name from. And following the Gambia study, the step wedge design in the years since has taken off big time, as discussed. And the term stepped wedge trial now covers a multitude of designs. And if you're like me, then you may find it useful to make sense of that multitude using a typology. Although when I put this to the cartoonist Chris Lysey, who was doing some cartoons for my Stepped Wedgehog website, he immediately came back with this cartoon. But I am someone who does like typologies, so I'm going to press on and show you a typology that, for example, I put forward in this key concepts article in the Journal of Clinical Epidemiology. So my first type of step wedge trial is what I'm calling a repeated cross-section design. I should say that in all of these diagrams, each layer of the diagram is a randomized sequence. And you can have any number of clusters allocated to each sequence, but in each of my diagrams, I've shown 3 clusters randomized to each sequence. The sequences differ to one another in terms of when the intervention is introduced in those sequences and in the clusters in those sequences. In a repeated cross-section design, which is my first type, individual participants are sampled in a series of repeated cross-sections, cross-sectional slices through time. And some of those cross-sections will be taken before a cluster has the intervention introduced to it. Some of those cross-sections will be taken after the intervention is introduced to a cluster. In contrast, we might attempt to design what I'm calling a closed cohort design, where we follow a closed cohort. We recruit that cohort once at the beginning of the trial from all of the clusters, and we follow the people in that cohort longitudinally over time, prospectively, assessing their outcomes at a number of predetermined time points over time. And some of those assessments of outcome will happen before the intervention is introduced to a cluster. Some of those assessments of outcome will happen after the intervention is introduced to the cluster. And the third type of design, in contrast again, is what I'm calling a continuous recruitment design. And in the continuous recruitment designs, participants present in one unbroken continuous stream over time. They present and are recruited and have an outcome assessed and then go away and leave. And in the meantime, more participants are presenting in a constant stream to those clusters. And some of those participants will present before the intervention is introduced to the cluster. Some of those participants will present after the intervention is introduced. And it's these continuous recruitment designs that I'm going to talk about today. So why might these need new ways of thinking? Well, for more on this, see this paper with Andrew Kopas, again in the Journal of Clinical Epidemiology. I want you to get away from the idea of time divided into a number of discrete time periods, which is a common way of thinking in step wedge trials. So I want you to suppose that there are no natural a priori divisions of time that we can divide the time scale into. Instead, I want you to think of the time scale as being one continuous scale of measurement. So what new ways of thinking do we need? Well, for one thing, we have much more flexibility in when we cross a cluster over to the intervention in continuous time. We're not constrained to cross a cluster at a boundary between 2 a priori time intervals. We can cross the cluster over at any point along this continuous scale of time, which gives us much more flexibility in terms of designs. Also, we may have to think more carefully about how we model intra-cluster correlations. This is a little bit more technical, but I'll try to describe. In step wedge trials where we have discrete time periods, we'll often assume that the correlation between outcomes of 2 individuals recruited in different time periods is weaker than the correlation between outcomes of individuals recruited in the same time period. But that intuition fails us if we have continuous recruitment. Because, for example, if I recruit 2 individuals just on either side of the crossover, because they're recruited close together in time, we might imagine their outcomes are more closely correlated than 2 individuals recruited at either end of some long nominal time period, because those individuals are more separated in time. So it may make more sense with continuous recruitment over a continuous time scale to imagine that the intra-cluster correlation decays continuously as the separation in time increases between 2 individuals. For example, we could use a kind of exponential model to parameterize that decaying intra-cluster correlation. Again, we also have to think about how we model the underlying fixed effect of time. If time is a continuous variable, that underlying fixed effect of time is a function of continuous time, and perhaps that's, for example, a smoothly varying function like a polynomial, in which case maybe we will see the intervention effect appearing as a step change or discontinuity at the moment the intervention is introduced, so that this cluster is effectively acting as a kind of interrupted time series here. But more than that, remember that we have a cluster randomized set wedge design here, so we may also have some clusters that remain in the control condition during that crossover, which we can use as a control for evaluating that step change that we can use to estimate the intervention effect. But we need to model the time potentially as a continuous variable here. Again, with continuous recruitment, we may also need to allow for a transition period between recruitment under the control condition and recruitment under the intervention condition. And that transition period may need to satisfy 2 requirements. First of all, we may need to allow time for the intervention to be implemented in a cluster to get it running at full strength. That may need some time to set up. But we may also need what I've called a closure period here. And the closure period needs to be long enough so that the last participant who was recruited under the control condition has either left the cluster or has had their outcome assessed, so that they cannot be contaminated by the subsequent introduction of the intervention. So we may need to allow a closure period there, and overall we may need to allow a transition period between those 2 intervals of recruitment. Thinking in a similar vein, we may want to consider more general incomplete designs. An incomplete design is any design where we don't recruit every eligible participant. We only recruit some of the eligible participants. And if there's a financial cost to recruiting each individual participant, or if for ethical reasons we want to minimize the total number of participants, then we may want to consider incomplete designs. We may want to switch recruitment on or off at different points along the timescale in a given cluster. In this example, I've switched recruitment on just before the crossover. We've got a few of the blue people there just recruited before the crossover, and then I'm switching recruitment off, the darker blue people, just after the crossover in this particular example. But if we have a number of randomized sequences and a number of clusters randomized to those sequences, and if we can switch recruitment on or off at any time we like along that timescale in each cluster, and if we can do a different thing in every sequence, we can potentially end up with some very complicated designs indeed. And if you were to ask the question, what's the statistically most optimal design for a given sample size, for example, out of all these possible incomplete designs? That's an interesting question, but it's an extremely challenging question to answer. And if there's time towards the end of this talk, I may tantalize you with some possible solutions to this design problem. Okay, let me talk briefly about some methods that I've used and that we can use to study optimal designs here. I'm not going to dwell in detail on this slide. It introduces some notation, something about the statistical model. You can return to this slide again later if you review this talk later on. But essentially, I am focusing on a continuous outcome measure here, Y. I'm including in my statistical model an underlying fixed effect of time, capital T, which is a function of the continuous time, lowercase t. There's a unit step function, capital H, which represents the effect of switching on the intervention, turning on the intervention in a cluster. And that unit step function is amplified by the parameter delta. Delta is therefore the treatment effect that we're trying to estimate, the effect of the intervention when that's switched on in the cluster. And E is a random error term added to the outcome Y. And however complicated the design that we specify, however complicated the model for the intra-cluster correlation, actually we can always work out what the variance of the treatment effect estimator will be using generalized least squares theory. GLS theory gives us a nice general matrix expression for the variance of the parameter estimators, which we can evaluate numerically if we need to. So if we have a particular design problem, we have a number of candidate designs that we're comparing, we can work out the variance of the treatment effect estimator for each candidate design, look at which is the minimum, and choose that as the optimal design. One simplification that I have made in all of the investigations that I'm going to show you is that I've assumed that in this continuous stream of participants, that each participant presents at exactly regular time intervals. So I'm assuming actually that the first participant presents at time 1 over m, the second at time 2 over m, and so on, up to the nth participant who presents at time 1. And I've chosen time units so that the entire duration of recruitment is 1 time unit. So this regularized simplification of the arrival process of individuals, well, it may not necessarily represent the truth in a real trial where participants present in a totally random process over continuous time, but it's a very helpful, almost necessary simplification to make to get started with evaluating and comparing different designs. And that's what I've done in the investigations I'm going to show you. So let's look at some design problems and their potential solutions. To start with a relatively simple design problem, which is a fairly straightforward parallel groups cluster randomized trial with a prospective baseline period. I'll show you what I mean by that. For more on this, have a look at this paper with Andrew Kopas in Clinical Trials. So what I'm imagining here is that we have 2 randomized sequences that we randomize clusters to. In the first sequence, clusters begin in a prospective baseline or run-in period where they're initially in the control condition. And at the end of that baseline period or run-in period, they cross over to the active intervention. And in the other sequence, the second sequence, clusters remain in the control condition throughout. And because this is a prospective baseline or run-in period, it's using up some of the time that we have allotted to recruitment to the trial. So it's using up, for example, time that we might be recruiting individuals under the intervention condition and learning about their outcomes. So the question arises, is it useful to have this baseline period at all, or should we just start people straight off in the intervention? And if the baseline period is useful, then the next question is, how long should that baseline period optimally be? Now, we looked at a variety of ways of allowing for an underlying fixed effect of time, firstly as a polynomial function, which might be linear, it might be quadratic, it might be cubic, and so on. But we also considered adjusting for the underlying effect of time as a discontinuous effect of time with a discontinuity at exactly the point in time where the intervention is introduced. Now, you might think this is an odd a priori choice for adjusting for a fixed effect of time. What we're doing here is this is actually a kind of a worst case scenario. What we're doing is playing devil's advocate and saying, what if there were an underlying discontinuity in the expected outcomes of individuals in our trial that happens to occur at exactly the same time that we introduce the intervention to half of the clusters? If that's the case, we're particularly grateful then that we have this control sequence where clusters remain in the control condition that we can still use to help us as a comparator to make an unbiased evaluation of whether the intervention is having an effect. But if there is an underlying discontinuous effect of time, that's a kind of worst case scenario for how that effect of time might be confounded with the intervention effect. Okay, and as I said, what we can do for different choices of crossover is use GLS theory to work out what the variance of the treatment effect estimator would be. So what I'm going to show you is graphs of the variance of the treatment effect estimator against the crossover on the horizontal axis. The crossover could be anywhere from 0, which is no baseline period at all, up to 1, which is a baseline period that takes up the entire duration of recruitment, which would be pretty pointless. And in this example, this is in particular for a value of m, the number of participants in each cluster of 100, rho, which is the intracluster correlation of 2 individuals recruited very close together in time, which is 0.05 in this case, tau, which is the decay in the intracluster correlation over the duration of recruitment, which in this example is 0.5. And I'm also assuming in this graph a linear underlying effect of time to adjust for. And this is the graph, and the minimum variance in this graph is actually attained at round about a crossover of 0.2 of the way through the recruitment period. If I were to assume a quadratic or a cubic effect of time that I needed to adjust for, then the shapes of the curves are very slightly different, and actually the minimum variance, the crossover at which minimum variance is achieved, is slightly different. So for a quadratic underlying effect of time, the minimum variance is around about a crossover of 0.5. For a cubic effect of time, the minimum crossover is around about 0.3. But I would nevertheless like to point out that these curves have a very similar overall shape. And they're all relatively flat, actually, between values of, say, 0.2 to 0.5. And if we increase the order of the polynomial for the time effect to quartic and quintic and sextic, we can see, again, very similarly shaped curves. And actually, the shapes of these curves are becoming more and more similar as we increase the order of the polynomial. And it's almost like they're approaching an asymptotic curve. And the asymptote that these polynomial curves are approaching actually is the variance curve for a discontinuous underlying effect of time. Now, there are reasons for that, but I won't go into now. But adjusting for a discontinuous effect of time, therefore, gives us quite a convenient kind of reference variance curve, which we know will be similar in shape to the variance curve for all of these other different ways of modeling the time effect, which overall look fairly similar. So although the minimum point of these curves does admittedly shift slightly, as I say, the overall shape doesn't shift very much, and it does suggest that this design problem and the solutions to this design problem are relatively robust to the way in which we estimate the underlying time effect, which we're adjusting for, which is a nuisance. And as I say, the variance curve for a discontinuous underlying time effect is a convenient reference curve that we might use for evaluating different choices of crossover time. This figure is taken from the paper. I won't go into this in detail, but it shows these variance curves for different combinations of parameters, different values of m. And in some combinations, we have a minimum variance achieved at a crossover of 0, which is no baseline at all. And in some of these curves, the minimum variance is attained at a crossover of 0.5, halfway through the recruitment interval. And in fact, we concluded overall in the paper that as a simple rule of thumb, you wouldn't go far wrong by always choosing between either having no baseline period at all or having a baseline period that was half the length of the recruitment period, whichever of those leads to the smaller variance. So these are relatively simple designs. It's a relatively simple rule. And to be honest, these two alternative designs are probably what a lot of people would already be doing in this circumstance without necessarily thinking very hard about why they're doing it. So that's quite a nice, simple conclusion about how we design these kinds of trials. But this talk is supposed to be about stepped wedge designs, not about parallel groups designs. So let's consider a more complex problem related to designing complete stepped wedge trials. And I hope you'll be able to read more about this in this manuscript led by Michael Grayling, which is not yet published, but we hope will be out soon. And I'm going to show you a particular example where, again, we have 100 participants per cluster. Again, I've assumed these regularized arrival times of those 100 participants at each cluster, arriving at time 1 over 100, 2 over 100, 3 over 100, and so on. Now, I'm also going to assume, rather idealistically, that I have a very large number of clusters. I'm going to assume I have many more than 100 clusters. And in that case, with these regularized arrival times of the 100 participants, designing a stepped wedge trial, that design problem amounts to deciding how we should weight the clusters over the 101 possible crossover sequences. That is to say, it amounts to working out what proportions we should allocate our large number of clusters to each of the 101 possible crossover times that can occur in this regularized arrival sequence. Now, this is quite a complicated design problem. Actually, the solutions are relatively complicated, and I'm going to do my best to try and take you through and characterize what some of those solutions look like. So this is a figure from the manuscript. Michael uses a slightly different parameterization to the statistical model that I showed you for my papers earlier. So rather than my rho and tau, Michael is using parameters rho naught and r. The parameter R is represented on the horizontal axis of each of these panels. And on the vertical axis, we have these 101 different possible crossover times. And this picture is a heat map. Each of these heat maps shows how heavily weighted clusters are to each of the possible crossover times. And where you see a bright line in each of these heat maps, that bright line indicates that a significant proportion of the clusters are being allocated to a crossover around about a very particular time. And that shows up as this bright line in the heat map. Let me try and illustrate that by taking a section through one of these heat maps. So if I take a section through in the middle row, that right-hand panel, where there are 3 bright lines, those 3 bright lines mean that what you end up with is the design I've illustrated on the right-hand side of the slide, where clusters are allocated to crossing over essentially at one of 3 different times. So around about a third of the clusters in this optimal solution are randomized to cross over towards the start of the recruitment period. Around about a third of the clusters are randomized to cross over halfway through the recruitment period, and around about a third of the clusters are randomized to cross over towards the end of the recruitment period. So it's more or less just a kind of a 3-step wedge design, and this is what turns out to be optimal for this particular combination of parameters. So you can see that with this small number of bright lines and the small number of steps in a step wedge trial that implies, even for a large number of clusters, we're getting some relatively simple looking design solutions. But one thing that I want to point out to you is that these design solutions depend very much on what the underlying effect of time looks like, which is in contrast to the situation with the parallel groups design with a prospective baseline, where I said that that design problem was relatively robust to the way that we model the time effect. Here, the solution does not seem to be robust at all to the way that we model the underlying time effect. So the higher the degree of the polynomial that we use to adjust for the time effect, the more steps we end up having to include in the optimal design. If we could believe that the underlying time effect was linear or quadratic, then we would get away with just having 2 steps in our step wedge, however many clusters we have. But if we believe that the underlying time effect is a quartic time effect, then we may need to include 3 steps. And if we believe it's a quintic effect, we may need to include 4 steps, and so on. So the number of steps that we need to include depends on how wiggly, how unsmooth we think that underlying time effect might be. The less smooth we think the underlying time effect might be, the more steps we should sensibly include in that step wedge design. Okay, let me talk now about incomplete step wedge trials. So these are trials where we can turn on or off recruitment at different times during the recruitment period. And for more on this, have a look at this paper with Jessica Kaser and Andrew Forbes in BMC Medical Research Methodology. And here's the illustration I showed you previously, where remember that we could turn recruitment on or off at any times we like during the recruitment period. And we can cross each cluster over at any time we like during the recruitment period. So there's a great flexibility in choice of design and a large number of different designs that we could compare. And actually, there are so many different possible designs here that it's simply not feasible. It hasn't been feasible to us so far to exhaustively search every single possible design. And because it's a very complicated design problem, it's also been infeasible for us to work out an analytical solution to write down the optimal design. So we haven't been able to prove what the optimal design is, but what we have done is to do a kind of a guided search through the design space, the space of possible designs, a kind of intelligent heuristic search through the design space to try to arrive at designs that we think might be optimal. Now in this next slide, I tried to sketch out what our search algorithm looked like, but I won't dwell too much on this because, in fact, the real algorithm we used was more complicated than this, and I've simplified, so this doesn't necessarily help. Just to understand that we did use this kind of a guided search through the design space to try to find solutions that we hoped might be close to being optimal. And I'm going to show you some solutions for the example with 30 clusters, each with 100 participants that we could potentially recruit over the recruitment period. The time effect is modeled as a 6th order polynomial in the particular solutions I'll show you. And suppose we want to find designs that achieve 90% power at the 5% significance level to detect the given effect size. So if we're looking for an effect size in this example of 0.15, a mean difference of 0.15 standard deviations, that is to say, then in this example, we actually need a complete design. We need to recruit all 3,000 of the available participants to detect anything like that effect size. So we need a complete design. And the crossover boundary is slightly sinuous in this optimal design. But otherwise we need a complete design. But if we can increase the effect size that we're looking for power to detect, we can get away with designing an incomplete design. We don't need to recruit every eligible participant. And here's the incomplete design we arrived at to detect an effect size of 0.2. And here the crossover boundary is more stepped. There are these macro steps appearing in the crossover boundary. The recruitment effort is concentrated very much in this broad swathe around the leading diagonal, although there is a little bit of recruitment taking place in these early clusters at the end of the recruitment period, a little bit of recruitment in those later clusters at the beginning of the recruitment period, which is unusual and perhaps not what we might expect to see, but we do see that strange recruitment pattern. Then if we increase the effect size we're looking for even further, to 0.25 and more, something very interesting starts to happen in the solutions that we're ending up with. What you can see happening here is that these solutions effectively consist of a number of distinct non-overlapping recruitment phases in different clusters. And in each of these 4 distinct phases that you can see here, there's very little or relatively little concurrent comparison between intervention and control. Most of the comparison between intervention and control is before the crossover versus after the crossover. And that crossover boundary is more or less just a vertical line, not allowing any concurrent comparison. And that's really interesting. So actually, each of these phases is really a little bit like its own interrupted time series with no control series to compare it with. Each is a standalone interrupted time series. And we're randomizing to one of 4 different non-overlapping interrupted time series in this proposed design, which is interesting and unusual. So I'm going to make some concluding remarks. As I hinted at the start, these are not necessarily conclusions, because I hope you can see already that these are very complicated design problems. And I think there's a lot more work that we can be doing on how we solve these design problems. But briefly, in terms of what I've shown you, well, in the simple case of a parallel groups cluster randomized trial with a prospective baseline, you can follow a simple rule of thumb. You can choose between not having a baseline period at all or setting your baseline period to be half of the overall recruitment period, whichever of those you calculate to give you a smaller variance. And as I said, this is probably what most people would already be doing in this design problem situation anyway. And we concluded we think that this design solution is relatively robust. So however it turns out you need to adjust for the time effect, whatever the form of the underlying time effect that you need to adjust for, that rule of thumb seems to hold good, and you still end up with the same design. If you're looking at a complete step wedge trial, well, you could take arguments from the results that I've shown you. There's maybe an argument coming out of that, but even with a large number of clusters, and even with continuous recruitment and time being a continuous variable, nevertheless, there may be an argument for keeping the number of steps in your step wedge small and allocating a number of your clusters to one step and a number of your clusters to the second step and third step, but keeping the total number of steps small. With incomplete step wedge trials, you may argue from the results that I've shown you that there are reasons for designing a trial as a series of non-overlapping interrupted time series. Perhaps this is a more contentious conclusion and solution. It sounds a bit dangerous to be suggesting that the best randomized design is an interrupted time series, but it's interesting to see that coming out as the optimal solution in this case. That we should randomize clusters to one of a small number of phases, each phase being its own interrupted time series. But in both the complete case and the incomplete case, these design solutions also depend on what we think the underlying time effect looks like. And the less smooth we think that underlying time effect might be, and the more wiggly and up and down we think that time effect might be, then the more steps or the more phases we should probably be including in that design. Now, finally, I've completely ignored in this talk problems with small numbers of clusters, which is a whole other talk. But just to briefly say to you, if you don't ever do a step wedge trial or any cluster randomized trial with a very small number of clusters, even if you have 30 or 40 clusters, which might be typical for many published cluster randomized trials, in statistical terms, that's actually still a small number. And if you have access to statistical software that will allow you to make a correction in the analysis for the small number of clusters there, you should definitely be using that. But as I say, this is a whole other talk, so I won't go into the details of that. I've ignored the problem. And as you saw, I've assumed in many cases that I have a large number of clusters to play with. This talk has been about design rather than analysis, and I've suggested that the design needs new ways of thinking, but the analysis equally may need not just new ways of thinking, but new software tools. If you're analyzing data using the models that I proposed, well, for example, you will need a software package that will allow you to model the intracluster correlation as a decaying intracluster correlation in the manner that I've shown you. Some software packages will currently allow you to do that. Some software packages currently won't allow you to do that. That may, even if it does, that may require some care in parameterizing and programming that intracluster correlation structure. But as time goes on into the future, software tools are likely to become more and more available and more easy to use for doing these kinds of analyses. Just as a shameless plug, we're running in London this year in November a 2-day conference on new developments in cluster randomized trials and step wedge designs, which well, you're welcome to show interest in. If you're interested in that, contact me or go to this website to get some updated details. I've included in this slide all of the references that I've cited in the presentation for convenience there for you to look at. And I've also compiled some other useful general references on step wedge trials in this slide here. That gives me lots of time, I hope, for questions. I think I've kept even to under 35 minutes. So I hope Dr. Murray will be pleased with that performance, and thank you all.
Thank you, Dr. Hooper, very much. Yes, you've left us plenty of time for questions and discussion, so that's great. So you've been focused in your talk on continuous recruitment, as opposed to the usual thing where we recruit folks either at the beginning of the study, everybody's recruited, and then we go forward, or we recruit different people at different times. And I just want to make sure that I understand how this continuous recruitment idea relates to some other terms that are used,
Sure.
including some that you have used. So in continuous recruitment, do we just measure each participant once, or do they get measured more than once, or could it be either way? How
Yes.
does recruitment relate to measurement occasions?
Well, that's an interesting point. And I should say, actually, that in real life, there's plenty of opportunity for real trials to fall between these types. No question that the reality is a spectrum, and a very complicated spectrum of how we can recruit and assess individuals. But what I'm imagining in my idealized type of a continuous recruitment design is that typically each participant is assessed once only. That may be almost immediately after they present to the cluster and are recruited into the trial. There can even be very long time delays between recruitment into the trial and assessment of outcome. In fact, that first ever stepped wedge trial, the Gambia hepatitis intervention study, is a really interesting example. In the Gambia study, there's continuous recruitment because they're recruiting babies as they're being born in the Gambia. So there's a continuous stream of newborn babies in the Gambia. That's a continuous recruitment process. The outcome that they were really interested in actually was cancer over a lifetime of those babies as they grew older into the decades. And they planned to follow each of those babies up maybe 30 or 40 years after they were vaccinated, and after they were assumed to have kind of left any sphere of influence within the cluster and contamination with other vaccination programs in newborns. So that's a really good illustration that the time between recruitment and that single assessment of outcome for each individual could be very long, compared with the timescale of recruitment. But nevertheless, their outcome is just assessed once for each of those babies at the 40-year point or whenever their lifetime cancer incidence is calculated. So that's what I mean by a continuous recruitment design, essentially, ideally, that you recruit and you assess outcome once for each person you recruit.
Thank you. And other terms that are sometimes used, cohort design, either as an open cohort design or as a closed cohort design. But I think both of those would be different from what you're talking about as continuous recruitment, because in each cases, participants could be assessed multiple times.
Yes, so of course, an open cohort design, which doesn't fall into the three types that I presented, is a much more flexible idea. In an open cohort, you don't necessarily follow each person in your cohort at every planned time point of assessment. They might drop out of the study, or you might recruit additional people further into the trial. So yes, an open cohort, which to be honest may be more realistic in many real trials, doesn't fit into the typology of the three types that I showed you. That's very true.
Now, in previous papers, we've seen pretty clear statements that increasing the number of steps increases the power of the trial. But if I understood your remarks today, that's not necessarily true with continuous recruitment. You found that a more limited number of steps often provided the optimal design, rather than always increasing power with more steps. Could you comment on that further?
Yeah, it's interesting, isn't it? And I don't think it's necessarily contradictory. And I think it partly relates to this idea of modeling the underlying time effect. So in a kind of more traditional, if you like, step wedge trial with discrete time periods, what we're typically doing is adjusting for a different effect in each time period, which is the most general kind of time effect that we could model. Whereas in these continuous recruitment designs, what I'm suggesting is that if we think of time as continuous, we might naturally try to model it as a continuous variable, perhaps to model it as a simple polynomial. I think it's that leads to the difference. So if we imagined, as I said, if that underlying time effect has a lot of ups and downs, a lot of stationary points, and it's wiggling about a lot, and we have to model it, for example, with a very high order polynomial, well, in that case, we would need to include lots more steps. And I think that's the point. That's where the additional power of the more steps comes in. It only comes in if we think we have to allow for this potentially very variable underlying time effect.
Is that related to the fact that time is usually modeled categorically in stepwise designs?
Yeah, exactly.
As opposed to continuously?
Yes. And I think if you looked at, I mean, I haven't looked at what's been written exactly on this question or looked at this question myself, but I think if you took the analogous situation of a discrete period step wedge design, then I think you should, in a way, actually, we looked at this a little bit in Michael Grayling's paper as well, and you'll see that when that comes out. That even with a small number of discrete periods that we model as a categorical adjustment, nevertheless, it may be that there's a benefit to having a smaller number of steps if we model the effect of time as linear or quadratic rather than as a categorical effect of time period, as you say.
Thank you. One of our listeners is raising a general question about this continuous recruitment. What if you don't have a constant rate of recruitment? What if that just, you're in the real world, it come in every 30 seconds?
Yeah, so I mean, firstly, this kind of regularized assumption of the arrival times, obviously that is a simplification. And in real life, you might imagine that participants are presenting as a random process in continuous time. Maybe you could model that as a Poisson process mathematically or something like that. So there's that simplification already. Now, in some situations, the group at Monash University have looked at simulating arrival processes that are not regularized, that follow random processes. And in certain situations, certain design problems, they've concluded it didn't make very much difference whether you made that assumption of regularized arrival times or not, or a more complicated random arrival time. So I'm slightly reassured by those limited investigations people have done that simplifying assumption isn't misleading us about optimal designs in the case of an arrival process that's actually random process in time, like a Poisson process. More dangerously, perhaps, we might have a situation where there's a trend in the rate of recruitment over time, over the entire duration of the trial. So maybe the trial starts with a very slow recruitment, and word spreads about the trial, and suddenly it's very much more easy to recruit people and recruitment rate picks up. Or maybe the reverse happens. And there, the assumptions that I've been making are thrown out of the window a little bit, and we would have to go back and rethink how that affects optimality of designs and what the optimal designs are. So there's another interesting problem to look at.
At the beginning of your talk, you spoke a bit about the strengths of the step-wedged approach, or at least the claimed strengths. And one of them was that everybody would get the intervention before the trial was over, and you sort of poked a hole in that, noting that in a parallel group randomized trial or cluster randomized trial, you could give the control arm the intervention once the data had been collected for the primary comparison, and then everybody gets the intervention, and the step wedge isn't the only one that can do that. Another supposed advantage is that investigators may be concerned that they can't roll out the intervention to everybody at the same time, or at least to half the groups at the same time. And the step wedge avoids that because it's a staggered rollout.
Yeah.
And certainly as recently as yesterday, I was making the case that you could have a parallel group randomized trial with a staggered start. So there's a study that we're working with that has 42 churches. Rather than trying to start the intervention in 21 at the same time at the beginning, they could take sets of 6, randomize 3 and 3, start the intervention in the 3, and once all of that is underway, move to the next set of 6. And after 7 of those sets, they'd be done, and they'd have it. So you can avoid that problem with a parallel design. So those
Absolutely.
those are 2 of the presumed advantages.
Yes.
Let me pause and see if you have comments about either of those points.
Yes, sorry to keep interrupting you. Yes, it's my excitement. Yes, I mean, you're right. And in the example that you just gave, what's interesting actually is that you could develop that design further into a multi-period design. So you could recruit your 6 churches, and instead of just assessing each of those 6 churches in one time period, you could have a baseline for all of those 6 churches, a baseline assessment, and then cross 3 of the churches over to the intervention and keep the other 3 in the control condition, and have a second assessment in that set of 6 churches. And now suddenly, although you've got a sort of a batched approach to recruitment and design, you've suddenly got a multi-period design within that batched approach, and that multi-period design could actually turn out to be more efficient. So I think there's wheels within wheels. You can still come back to the question of, can you improve efficiency by adding multiple periods? And there may be pros and cons of doing that.
And what you propose is exactly what is under consideration for that trial. So there would be a baseline in all 6, and then randomization, and then a follow-up after a period of time, and potentially additional follow-ups after that.
Yeah, that's interesting.
Yeah. Another claimed advantage of the step wedge is this better efficiency compared to the parallel design, and I appreciate that is true under some conditions, not necessarily true under other conditions. But I think the other 2 presumed advantages probably don't hold up. One of the weaknesses of the step wedge design that I've been concerned about is that it is sensitive to the impact of external events, because as we go along in the step wedge, we run out of groups that are in the control arm, and we have everybody in the intervention arm. So if something happens, especially late in the trial, that could affect the outcome that has nothing to do with the intervention, that could be more problematic in a step wedge design than in a parallel group randomized trials design. Does your continuous recruitment have any bearing on that concern, on that problem with step wedge designs?
I mean, I guess it could be affected in the same way. I mean, of course, we can, because it's very important to adjust for secular changes over time in some way, in some respect. It's very important to do that in some way because precisely because secular time changes are confounded with the intervention effect in any step wedge design. So to some extent, we get around that problem by the adjustment for the effect of time, and we have to work out how we're going to model that underlying effect of time. And that's behind a lot of the discussion that I've been putting forward today about how exactly we do model that underlying effect of time. I suppose more seriously, you might have situations where a step wedge trial has to be abandoned early on because of issues. And then you're left with a kind of imbalanced design where you haven't had time to recruit many people in the intervention condition. And again, I think that would be a more of a disaster for any type of step wedge design. I think as long as you feel confident in being able to adjust for the underlying time effect, the point of a step wedge design is that you can make that adjustment and still make a valid estimate of the treatment effect estimate.
Right. I just think that gets more complicated if there's an external event, because you may not have many control observations to let you estimate the impact of the external event separate from the intervention. An assumption that I think you've made is that the underlying time effect is the same in every cluster.
Yes.
Yeah.
Yes.
What if that's not true? What if the time effect is different?
That's a really interesting point. Yeah. So of course we can make, and I've chosen a very simple analysis model overall anyway. And with these models for step wedge trials, you can start to make them as complicated as you like, really, and introduce more terms. And certainly one thing that interests a lot of people is whether we should try to model a different time effects in different clusters. I think whether we do or not, for me, there are different ways of doing that. I think in any case, it's useful for me to try and model a consistent effect of time in all of the clusters, just in case there is one present. I think it's useful to try to adjust for that, to rule it out as a possibility or to have adjusted for it. And the model for the intracluster correlation that I've adopted in my models, where the intracluster correlation decays with increasing separation in time, one of the consequences of that model is that what you get in different clusters is different looking trajectories. Because with increasing separation in time, you can less easily predict what the end of a trajectory in a cluster will look like. So in different clusters, different characteristic trajectories of outcome tend to move in different ways and diverge and follow different paths. So even that intracluster correlation model does effectively allow for a kind of a random variation in exactly what the trajectory looks like in each cluster. So implicitly, I have actually allowed for some variation in time effect within different clusters, even in my simplistic model. And I do think it's important, nevertheless, to have adjusted for an overall fixed effect of time, just in case there is one. But yes, absolutely, this is a question of great interest. To what extent it matters whether we leave out this interaction between cluster and the time effect, if there is one there, and how we incorporate that into our models. These are really interesting design questions and analysis questions.
And one that's quite related is what if the treatment effect is different in some clusters compared to others? And that's actually pretty plausible in many circumstances.
Yeah, indeed. So you could model a random effect of treatment between different clusters on top of the kind of overall fixed effect of treatment. That's an additional sophistication that you could add to the model. And I haven't looked at that in the investigations that I've shown you, but of course, again, this is a great interest to researchers to what extent it matters whether we include this or not and what difference that makes to optimal designs and how we should analyze trials. So yes, these are very much open and big questions.
One of our listeners asks, in a continuous recruitment design, is there gain in efficiency by having additional steps when everybody gets the intervention? I suppose that would be additional steps at the end of the trial.
Yes. So actually, I mean, in discrete time period step wedge trials, you often find there's no advantage at all to having a kind of initial period where everyone is in the control condition or a final period where everyone is in the intervention condition, because that doesn't allow you any concurrent comparison of intervention and control at all. So often that isn't very helpful. In the optimal designs that I showed you in the specific design problems that I'd investigated, actually there were initial periods of the recruitment period where we had everyone in the intervention in the control condition. and periods towards the end of the recruitment period where everyone was in the intervention condition. And that's partly to do with the fact that we're assuming this complicated intra-cluster correlation structure. So actually having people assessed in a kind of run-in baseline is useful as a kind of where people are acting as a control for themselves, if you like, so that you can learn something about those individuals at baseline, even though there's no concurrent comparison with controls. So it's naively, you might think there's no point at all in any step wedge trial in having that initial period where everyone is a control. But actually in some situations, in some design situations, there is an advantage to having that initial period where everyone's in the control. Does that answer the question?
I think so. Someone has been looking at your blog posts and found advice about not doing a step wedge trial unless you're sure that you really need to do a step wedge trial. So I'm gonna pose the question based on that supposed quote from your own blog post. If you've got a circumstance where you're considering a parallel group randomized trial or parallel cluster randomized trial, whatever label you want to use, versus a step wedge, and your preliminary work suggests that there's not a great deal of difference in efficiency, that you're going to need about the same size study either way, which one would you go with?
In many cases, I would try to steer investigators towards the simpler parallel groups design. It's rather similar to the situation with cluster randomized or group randomized trials. As statisticians on trials or statisticians advising researchers, we tend to recommend that people don't do a cluster randomized trial at all if they can do an individually randomized trial. And similarly, this is my motivation, despite being an expert supposedly in step wedge trials. This is why I tend to recommend to people not to do a step wedge trial unless they absolutely need to, because the additional complications of running a step wedge trial can be infernal. Getting the different clusters to comply with this more complicated schedule for the trial, for example, may be extremely difficult to do, and it's quite difficult in reporting and analyzing that trial to know how to cope with non-compliance with that rather complex schedule that you assign people to. So the additional practical complications that you introduce, you really have to weigh against any small advantage you might be introducing in terms of statistical efficiency.
Yeah, I must say that I agree completely with the assessment that you just provided. When I was at university as a professor, I would regularly advise against group randomized trials and in favor of individually randomized clinical trials if they could deliver the intervention without substantial risk of contamination. And if contamination was a real threat, then yes, let's figure out how to do the group randomized version and do it well. And these days, I find myself arguing for the parallel versus the step wedge because of their relative simplicity and avoiding some of the threats that I think are greater for step wedge than for parallel. So I think we're on the same page. I wanted to pose one last question, and I raised this with you before the webinar started so that you might have a little time to think about it, even though you've been presenting the whole time. So we've got this recent paper from Kenny et al. Out of Jim Hughes's group at Washington. And Jim Hughes spoke about it on his Mind the Gap webinar a few weeks ago. And it suggests that if you've got a treatment effect that varies over time, so it might gradually develop and hold for a while and then fade again. That's a common pattern that we see, especially with behavioral interventions. If you've got that kind of pattern, but you use almost any of the analytic models that have been presented in the literature for step wedge designs, you can get a terribly biased or inaccurate treatment effect estimate and standard error for the treatment effect estimate. And he offers some ideas for ways to deal with that. But I'm not sure if you've had a chance to study the paper. I just wondered if you had any thoughts about that issue.
Yes, it's interesting that it kind of became canonical very early on in the step wedge trial literature that models would assume that the effect of the intervention was maintained once it was introduced at exactly the same level. And of course, perhaps that always was a slightly questionable assumption. I mean, I suppose people were thinking that if you're making a kind of policy change at a cluster level, then once you've introduced that change, it might be reasonable to think that every individual who comes along and is affected by that policy change responds in a kind of way that's maintained ever after. But I mean, I wonder really how realistic that assumption ever was. And so naturally, this has become an assumption that people are starting to challenge. And it's one more way in which people are starting to stretch the analysis models that have been proposed. And I think in some ways we're in a difficult position at the moment where we're still learning as statisticians, as researchers, co-researchers and advisors. We're still kind of figuring out what we should be recommending as standard practice. We're still in a state where people are constantly adding terms to the proposed model, all of which look perfectly reasonable, and we start to wonder when it will ever end and how we can trade off ways to advise people on planning and analyzing studies and how we should actually be analyzing them. So I think this is a difficult time, and we don't necessarily know what's right and wrong at the moment. But certainly, lots of people are stretching the existing canonical models for analysis in interesting ways.
Yeah, yeah. Well, I want to thank you very much for a terrific presentation and discussion. We are at the top of the hour, so I'm going to turn this back to Dr. Moyer.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. You will receive an email with a link to the recording when it is available. Thank you and have a great rest of your day.